All right, and once again, good afternoon and welcome to today's webinar, which is the Simulation-Aided and Simulation-Guided Testing webinar. My name is Mark Musitano. I'm Senior Sales Engineer over here at DFR Solutions. With me today is one of our senior staff members, Jim McLeish, who will be presenting today's webinar. Just a few housekeeping items before we get started here. This webinar is being recorded, and we will make it fully available online at dfrsolutions.com within the next few days. At the end of the webinar, Jim will also show his email, and if you're interested in getting a recording of the webinar immediately, you can go ahead and email him and he will pass that along to me, in which time I can get you a copy. Also, all lines are going to be muted during today's webinar except myself and Jim's line. If you have any questions that you would like us to address, please go ahead and write them in the questions box on your GoToWebinar viewer, and we will address them at the end of the webinar. So with that, Jim, why don't you go ahead and take it away.
Greetings, everyone, and thank you for joining us today on a webinar that will be providing information on the latest advancement. Excuse me. Mark, could you mute your line, please?
My line is muted.
We have somebody cutting in
Maybe
there.
somebody else's.
Okay.
All right, I think we're all set.
Okay, we'll try this again. Greetings, everyone, and thanks for joining. I'm Jim McLeish. I head the DFR Solutions office in Southeast Michigan, where we do a lot of automotive and some military-related products. I used to be the electronic reliability manager at General Motors, and I was a member of the team that developed and calibrated and wrote the GM test standard for qualification of electrical and electronic embedded modules. I'm also on the Society Automotive Engineering Electrical Electronic Reliability Council and have been involved in a number of SAE standards. So today we'll be talking about the leading edge technology for developing and optimizing accelerated reliability, durability, demonstration life tests. It's the new world of simulation and test integration, what we like to call simulation-aided testing and simulation-guided testing. We'll be explaining the differences between those two approaches here in a few minutes. So, as many of you who work in various forms of the electronic industry know, there are many guideline documents and standards on the various environmental conditions and static and dynamic stresses they can apply that electrical and electronic equipment need to endure. And these documents also provide recommendation on how to apply functional performance and reliability, durability, life qualification tests in order to demonstrate that your electronics will not be disrupted or malfunction or outright fail when they have encountered or must endure over a long period of time the various types of environmental and usage stress conditions. So some of these standards that are very popular for many are like MIL Standard 810, environmental engineering considerations and laboratory tests as they apply to military and defense equipment. Then SAE J Standard 1455, environmental practices for electronic equipment in heavy-duty vehicles. IPC SM 785 defines accelerated reliability testing methods for surface mount soldered components. And ISO 16750 is road vehicle environmental conditions for electrical and electronic equipment, the European standard. And there's also the IEC 60068, which is a series of numerous, I think 40 or 50 different environmental testing methods that can be tailored for various applications. So each of these documents provide valuable information on the types of environmental conditions that can be encountered in various types of applications of electronics. As everybody pretty well knows, electronics has infiltrated into every parts of our lives, in vehicles, in our telecommunications, in our entertainment systems. Our whole society is built around electrical electronic technologies. And it's been well known that environmental stresses can disrupt electrical electronic equipment performance and reliability, and that the equipment needs to be designed to cohabitate with the various electrical stresses or environmental stresses that are out there. So these documents also provide recommendations on how to simulate these conditions in performance and accelerated life testing formats. However, they're not complete documents. Each of them advises that a significant degree of tailoring is required to adapt the stress level information to a specific application, and then to correlate the duration of the test to the intended service durability life of whatever product or system you're working with. So these documents are a very good starting point for developing a reliability durability qualification test plan for some kind of EE components or systems, but they are not complete requirements. Like I said, each of them advises a significant degree of tailoring is needed, and organizations that are interested in developing a test plan still need to determine the test duration, either time on test or number of test cycles, the pass-fail criteria, sample size, how many samples are necessary to provide the demonstration of the desired reliability requirement, or at least a reasonable conclusion about how the product will behave in the field. And this is needed so that your suppliers can provide the needed number of prototype parts for the test, and that lab personnel can determine the amount of test equipment that will be needed. So all of these are the different aspects of test planning that need to be considered and communicated. So now, one of the primary tests that is done for electrical electronic durability is thermal cycling to do solder fatigue. And we now have some very accurate math models for solder fatigue calculations. They started with the Engelmeyer model, which has been modified a number of times for determining that thermal cycling induces or transmits a stress into a solder joint that produces a shearing force, and then figuring the strain energy dissipated in the solder joint, which can lead us to determine the mean number of cycles to fail. Another important issue about thermal cycling is the plated through hole cracking of the vias in the circuit board. The circuit board in their z-axis expands and contracts significantly more, usually 4, possibly 5 times more than they do in the XY plane, where they're constrained by fiberglass fabric weave. If there is excessive expansion in the z-axis, you can fatigue the plated through hole copper vias that are used to provide electrical signal communication from the top side of the board to the bottom side of the board and any interior layers that it's connected to. There was actually quite a bit of work by the IPC to develop this model. So these provide information that can be used to figure out how units need to endure in the field. There's many challenges to developing accelerated life tests because there's so many different applications where electronics is used, as I mentioned before. In the defense and aviation industry, it's typical to see electronics are being specified to last for 20 to 25 years in a very dynamic and mobile high-stress environment. For industrial, power, or telecom structure equipment, the usage life is typically 15 to 25 years. In a field environment, though this is often outdoors and exposed to the various elements. The usage life for passenger cars and light trucks is typically 10 to 15 years of environmental exposure with 100 to 200,000 miles of usage. And when we look at commercial heavy-duty trucks, the usage life is again usually 10 years of environmental exposure, but at least 1 million miles of usage. So these are some of the different challenges that different industries need to do when they are considering how robust their electronics need to be for their application and how they can go about proving that. Now, the classical approach to life test correlation that I actually was involved in quite a bit at General Motors, it took us 2 years to get the information to qualify the environment that automotive electronics endured either in the passenger compartment, under hood, or in the chassis. And the way we did that was that we would start by harvesting similar electronic components from vehicles that had been in service for a significant amount of time. And often this involved getting the parts out of junkyards and finding out what we could about those parts when they were produced, where they had been used, when they were put into service, what kind of climatic stresses they were seeing in whatever part of the country or world that they were operating in, and figuring out the exposure time and operating cycles that these devices endured. The next step would be to take these harvest modules and do both non-destructive and then destructive laboratory evaluations of the field age devices to characterize the types and degrees of aging degradation they had experienced. So this would be things like corrosion, wear on the connector terminals, fatigue of solder joints, delamination of the circuit board, things of that nature, to figure out what all of the different components in an electronic device had experienced. The next step would be that we would run accelerated lab test experiments on similar materials or specially prepared test sample coupons. And periodically we would pull these things off of whatever test they were going under, and we would repeat the degradation characterization evaluations to find out what degree of aging degradation we had produced at this point in the test. And our objective was to eventually determine what length of testing under specific conditions would be necessary to produce an equivalent amount of degradation aging in the lab to what we saw in the field. And this typically could be a 2 to 3 year expensive effort for each item you wanted to investigate. And there's a very good paper that documents this approach. It's called Lab Field Correlation for Automotive Electrical Connectors by F.W. O'Malley. And he was in Delphi Automotive, which was made up of the former GM Delco Packard Electric wiring and connector division. And this document was published in Electrical Contacts 2000, the proceedings of the 46th IEEE Holmes Conference on Electrical Contacts. And you see I give you the catalog number and a link if anybody wants to look up this document and get more information on this type of approach. Now, that was a very long and expensive way to figure out what you need to endure and correlate your test. Physics of failure research now has made a faster and more accurate way to develop accelerated test-to-field correlations. So physics of failure is also known as reliability physics. It's a scientific approach to failure research that identifies the failure mechanisms of how and why failures occur in various devices, materials, and products. So this research has been producing math models of aging wear-out failure mechanisms for various types of electrical, electronic components and materials. And this gives us a scientific basis for evaluating usage life and hazard risks of new materials, structures, technologies, and products under actual operating conditions that can be done in a virtual environment rather quickly instead of the years it takes to collect and characterize parts in the way I just described. So the development of failure mechanism models have since been incorporated into a computer-aided engineering software program that can perform durability simulations on new designs of electrical, electronic equipment in a virtual environment rather than a physical environment, which means we can do it in a day or two once we have all the information rather than spending weeks, months to years. So to determine the rate of damage accumulation of materials under stress that can identify when the failure point of an item is reached and the reliability of a product as they age under either field or test usage and environmental conditions is what we are aiming to do here. And we'll be describing how we can do this and do the simulation under both the expected field surface life usage conditions and compare that to a design of experiments, if you will, of various test configurations in order to come up with a test that produces an equivalent amount of stress-driven damage aging that would be experienced over the intended design life in the field. So to explain the basics of the physics of failure approach of how things age and wear out, which is based on the material science principle of stress-driven damage accumulation in materials. We have a little example here. So let's assume that we have some structure, and let's face it, electrical components have to be packaged in a physical world in an integrated circuit or a chip capacitor or a relay terminal capacitor or an inductor. There's a structure there that's holding all of the wires and leads and terminals and electrical active elements together. So any kind of structure is going to experience loads as it interacts with the real world. So I'm using here an example of a simple physical structure taking a load force. But when we talk about loads, it could be any kind of physical entity. It could be electrical, chemical, thermal, mechanical, et cetera, et cetera. It doesn't have to simply be a weight load-bearing type member, as I'm using here to simplify this example. Now, whenever a structure is loaded, stress is created and transmitted throughout that structure. And as materials are stressed, they are also strained, which means there's an instantaneous change in the materials and its structure due to the effects of a loading condition. So what we look to understand in physics of failure research is knowledge of how and which key loads act or interact to affect the product, and we want to use this information for effectively and efficiently developing good products, processes, and evaluation methods. So as materials are strained, they can be damaged or degraded. Now, if materials are strained in what's known as the elastic region, like a rubber band, you pull it out, you take it, and then you release it, it snaps back or relaxes back to its original state. But after the elastic region of a material's characteristics, there's what's known as the plastic response region. In the plastic region, you get what's known as plastic deformation. When you apply a load to something, it initially is stressed and strained, but when you remove the load, it does not come back to 100% where it was at the beginning. So it might be 99.9999999 of its original condition. And then you provide another stress cycle or another hour or so or day or so of stress exposure, and now it's 99.99998. So that's what we call damage accumulation caused by plastic deformation as the materials in our electronic products are loaded and stressed and strained. Now, from this, we kind of realize that there are going to be various sites and types of failures that will occur faster than other locations. And this is because, and we look for things we call stress concentrators, where multiple stresses combine and interact in stress materials, or a design weakness that was a unintended weak point in the design, such as where a circuit board trace might be skinnied up to get it through a narrow passage of components. And that skinnying down or pinch point is going to become a hot spot if that trace has a high enough current load. And then we also have to worry about material and process manufacturing variation from making strong parts to weak parts, and sometimes that goes to the extreme of some of the parts may be totally out and out defects. So what we do for understanding this load stress strain damage accumulation relationship is calculate how strains are transmitted across the circuit board to all of its components, and then what are the features of those components that are stressed and strained. And we can calculate the mean time to failure of them. And because we also have physics of failure research about the distribution, about the mean, Weibull slope analysis, we can then figure out the distribution along our calculated mean in order to come out with what is the time to first failure, and then what is the rate of degradation that will be occurring after that. Now, this is a significant advancement over where reliability prediction has typically been, where we have been limited to calculate the mean life. But the mean life means 50% of our products have already failed and 50% are still working. But what we endeavor to do here is define the all-important time to first failure in order to ensure that we can design our products so that the environmental and usage conditions they are going to be exposed to make none of the parts fail, or as few of them as possible. So the tool that we use for doing that is what we call the Sherlock Automated Design Analysis tool. It's a computer-aided engineering app. Now, we all know about apps on our smartphones and tablets that take a specific feature and highly automate it so we can get a piece of information very, very quickly, whether it's finding a restaurant or getting the local weather or checking your stock market. And instead of having to push a bunch of buttons, there is a little mini program that defines exactly what you need to do to get information or a function that will be useful for you. And that's what is now happening with computer-aided engineering. Apps are moving into this realm as well. Used to be to do some kind of finite element or thermoanalysis, you needed a highly experienced person in the modeling area who also understood the products and what they were modeling thoroughly. And usually this would have to be a PhD or near PhD level person. But what we have done in the Sherlock tool is automate the model creation tasks in order to allow frontline electrical engineers and their circuit board layout designers to not have to worry about all the details of creating a model correctly. We just let you provide the information about your design. It creates the model. You then provide the information about the conditions the design needs to endure, and it goes from there. And to show you that, the way we create the model is we have a design capture feature where the standard circuit board design files in either the traditional Gerber format or the new circuit board manufacturing data archive, the OBD++ format, can be imported into the program along with the part BOM list and the circuit board fabrication drawing. And we take all this information and look at how thick the board is, how many layers it has, what insulation material it has, how much copper trace and conductors it has, how thick they are. And first we create a virtual model of the circuit board, because the circuit board is the foundation that your electronic product is going to be built upon. And it determines how stress is going to be transmitted to many of the components. And we then take the parts list and correlate that with a built-in library of all the different component models, and we use the circuit board pick-and-place build file in order to say each component goes at this location and is connected to these solder pads. And that's how we create a rapid 3D model of your specific circuit board design for your electronic product. The next step is to go into our lifecycle manager and define the environmental conditions that this device is going to be required to endure. So this can be your vibration profile, it can be seasonal, daily, annual thermal exposures, it can be usage, product self-heating. All of these things can be captured in the life cycle definition and added to the model. Once we've done that 2 steps of the model creation process, then the fun begins. We hit the magic button and the load transformation occurs. A finite element model is created to calculate and distribute the environmental and operational loads and to stresses and strains to all of the components and features on the circuit board. Then we feed the component information and the stress information that it is enduring into the physics of failure durability simulation models, the failure mechanism models. And this is where it comes up and says, this part enduring this kind of stress profile for this long is going to degrade to this point. And what we do is produce a number of different types of charts and plots and analysis that show you when failures are expected to occur and what kind of growth rate they're going to occur at for each kind of failure mechanism your product is susceptible to. And we also then come out with a Pareto list saying which parts are going to fail first, second, third, fourth, fifth, and why. And so this is the equivalent of doing a physical test where you get failures and the test agency writes you a test incident report and you get information of what failed and why, and you as the product engineer have to eventually do some form of root cause failure investigation or analysis, figure out why it failed, and then figure out how to enhance the design so it will not be susceptible to these kind of failures in the field in the future. So that is your traditional design, build, test, fix, reliability growth approach. We have moved it into the virtual environment where you can do virtual validation durability testing in an afternoon under various conditions, one after another, to see how reliable your product will be in a virtual environment. And you would then just treat the simulation failure result reports as you would your physical test incident reports. And you say, oh, this part is failing for thermal cycling and this part is failing for vibration or whatever have you. And then you can go in and figure out ways to optimize the design to remove its susceptibility to failure only instead of having to do a new design and build a new set of parts, which would, take you a couple months, and then run another 16 to 20-week test to see if you were successful or not, you can interact and make changes in the virtual environment while it's still in the Sherlock tool, and then rerun it in another couple minutes and see if you fixed the problem or not. And the intent is that you keep doing virtual design optimization until you come up with a highly robust product. So now, many of you who have been in our past DFR Solutions webinars have heard us talking about the Sherlock tool and how it can be used to produce highly reliable, robust product design. Now, what is lesser known is the simulation test integration aspect, is that once you have this model of your design and you optimize it, you can also use it to develop an application-specific optimized accelerated life test. Now, the first question you might ask is, well, if the design has already been optimized for reliability, durability, why is testing still needed? Well, again, before we used to do traditional life testing in a design it, build it, test it, see what broke, fix it, reliability growth process. And that was the only way possible to achieve reliability and durability. And this would often require round after round of design, build, test, fix. With Sherlock, we can now virtually optimize the design for reliability and durability, but it's still necessary to verify that your suppliers and the assembly processes are building and producing to the designer's expectations that were used in the model. So if you have a some kind of insufficient part coming in through your supply chain, because purchasing bought it from the lowest cost manufacturer producer as opposed to the most robust version of the IC or resistor or whatever, that's something you need to determine. Same thing in if your circuit board assembly process has been optimized or not yet, or if it still has problems. So you'll still want to do some degree of testing after a virtual product optimization to make sure that your supply chain and processes are producing to the designer's expectations. However, as we now have a virtually optimized design, the testing no longer needs to be as extensive as it used to be. We now can develop application-specific optimized testing that can be run faster and be more effective at detecting if durability, reliability, defects, or issues do exist. And this can be done in conjunction with the test optimization. Again, once you do the physics of failure, Sherlock modeling to optimize the product under either your field or test conditions, then you just do it the opposite way. And we're going to get into that here in a minute. So the next question might be, why is application-specific evaluations needed? Okay. Well, the truth is a circuit board assembly with hundreds of different kind of components on it is a complex product, and each of those components has their own characteristic life. Now, when I got into electronic designs way back in the 70s, and some of the first automotive electronic products, there were a lot less components to choose from. All the ICs were in what was called the DIP package, dual in-line lead-in package. And they all went through a circuit board with a plated through hole. And the early testing seemed to indicate that there was pretty much this universal acceleration factor. But that really doesn't exist with today's electronics with so many different types of parts and package types. So it has been very easy to take one component and put it on a test coupon and develop a very effective accelerated life test. But that won't transmit to the same component being on a different circuit board with different material properties and stress transfer characteristics. and you then put a different kind of component next to that. Those things will work out. So why accelerated testing can be done on a single item and single failure mechanism approach. Developing a repeatable life test for a complex electronic device is possible but challenging. And that's where we've come up with the simulation-guided simulation test method to help that out. And another thing you got to be worried about when you design a test is that you don't design an accelerated test that is so accelerated and overstressed that it winds up producing what we call foolish failures. Foolish failures are failures that would occur because we are over-testing, and they would be something that we would never see in the field. And it's very frustrating to have a foolish failure situation come up because you have to investigate them just as you would any other test failure. And then it's actually harder to prove that this failure is not going to be something you would see in the field than it is to look at a failure that you know would fail in the field. And we'll be talking about that a little bit more in a minute or two. So again, why is application-specific testing needed? Well, it's because, as I just said, there's so many different sizes and components with different coefficient of thermal expansion characteristics relative to the circuit board that they're attached to. There are many different kinds of component attachment systems: leaded component, ball grid array, bottom terminated, flip chip. All of those have highly different durability life characteristics that we'll be showing here. The size of the component and the size of its solder joints and pads. The fatigue characteristics of the solder material that's being used. We know that today's lead-free solders take higher temperatures and will take more thermal stress than the old tin lead solders we used to use. However, they're usually more susceptible to fracture than they are to fatigue. And then there's always the quality of the soldering. Did you get good solder joints with a good metallurgical bond and adequate bulk to give you the desired degree of attachment strength? Also, you got to think of all these things about the components relative to the coefficient of thermal expansion of the board they are attached to, which is determined by the material properties of the base laminate material, the type of fiberglass fabric weave that is used to constrain the thermal expansion characteristics of the base laminate, and to also provide structural strength against vibration and shock. The amount of copper and the layout of the copper on each conductive layer, how thick it is, where it goes, what that adds to the performance of the overall board, and the thickness of each insulating and conductive layer. So this is what we all call the circuit board stack-up analysis, which we can do to tell us how a specific fabricated circuit board will behave after it has all of the design features needed to do the function it needs to do. So to illustrate some of the differences about the different kind of component packages, when I got into electronics, we were using low-cost single-sided circuit boards with leaded components. So I got the little arrow here pointing to this upper left-hand corner dip chip where the lead goes through a hole, and on the back side of the board there's a solder pad that gets a little dab of solder from a wave solder to make the attachment. When we were producing automotive electronics with these kind of boards, we would start to see failures occurring after 1 to 2 years of use on the vehicle. Now, back then, vehicles were only warranted for 1 year, 12,000 miles. So it was the vehicle owner, the customer, who wound up experiencing a lot of failures, and he'd have to buy an expensive replacement module, which was only available usually from the automotive dealer at high cost. And that made for a lot of unsatisfied customers in the early days. Now, As electronics got more complex and we needed more circuit connections, we had to go to the more expensive circuit boards with double-sided circuit features on both sides of the board, and the circuit features were attached by a copper-plated through-hole known as a via, because the electrical circuits would get from the top side of the board to the bottom side or vice versa via that electrical through-hole plated connection. Now, when these parts were wave soldered, the wave would fill up the entire thickness of, or the entire length of the copper plated through-hole barrel. And this produced this big slug of solder that made for a much stronger solder joint that would be 10 to 15 times more durable than what we had before. When we went to the more complex double-sided plated through-hole circuit boards, our reliability, our durability just skyrocketed. And nobody could understand this because the reliability experts at the time were using the now widely discredited Mill Handbook 217 reliability prediction by part counting and tabulation of the generic failure rates of generic components. And they didn't care why it failed, they just cared, oh, well, that part failed, so we're going to give it a black mark. Well, they didn't account for the fact that components were failing because they had weak attachment systems, weak solder joints. And when we produced the stronger solder joints, our reliability greatly improved, our durability greatly was extended. And we were very happy with this for a few years until in the late 80s, early 90s, this new technology called smaller surface mount components came out. So we always want to put more components per square inch on a circuit board. That reduces costs, and circuit board designers get their credit by how tightly they can pack components in. So the fact that these surface mount J-lead components had a lead that swung underneath the body, took less real estate on the board, was highly desired at first. Except these leads were very stiff, and now we went back to attaching them to a pad instead of a through hole with a little dab of solder that was less than what we had with the single-sided plated through holes. Well, guess what? Thermal expansion, contraction, and vibration, these little leads were like rocking chair legs. They rapidly wiggled out of that little tab of solder joints, and we would start to see failures a little bit after a year of vehicle usage. So this was an absolute disaster for us, and it wasn't just for the auto industry. This happened in many industries. The IEEE put together what they called a compliancy task force to look at the issues of stiff leads fatiguing themselves out of these little solder joints, and that led to the development of a second generation of surface mount electronics where they had what was known as the fine pitch gull lead, gull wing lead. So here we have a lead with two bend points, and those bend points basically allowed the component and the circuit board to move relative to each other. The lead was like a spring that would allow relative motion instead of transmitting all the micromotion stresses into the solder joint that would produce rapid solder fatigue failures. And we would get these to last 10, 12 times longer than the J-leaded solder joints in life. Then, of course, the package technology kept changing. We went to smaller and finer solder pumps and then high-density bulk grid array devices. These, in their early days, also had problems until we developed methodologies to reduce the stresses of the solder balls to get their life up. And what we have today is the onslaught of what are called near chip scale packages, leadless, bottom terminated component, quad, fine, no lead, dual fine, no lead, so on. All these products were designed for use in today's mobile, tiny, lightweight, handheld, portable electronics. And when you're selling like 36 million iPhones a month, the IC industry notices that, and they start making everything they make in these kind of packages. So as these packages are become the only things available to electronic designers, where I use the new phase chip, they got to figure out how durable they'll be in high reliability applications, because they were developed for cell phones and tablets that basically are used for maybe 2 to 3 years max before you replace it with a new, hotter, cooler, more functional version. So this next slide shows us exactly what is the ramification in terms of durability life and thermal cycling of all these different package styles. So with the gull wing leader components, we can typically achieve a mean life of more than 10,000 thermal cycles from -40 to 125 degrees C. But a BGA, depending on the size, that will drop to 3,000 to 8,000 thermal cycles of -40 to 125 C for the mean thermal cycle life. But these QFN or chip scale packages are only good for 1,000 to 3,000 thermal cycles. Now, again, that's their mean life, which means there's going to be a distribution about that mean, and the tail that defines time to first failure of that distribution can be problematic in high reliability applications. And this has actually been a problem for a lot of automotive electronics as these new bottom terminated fine chip scale packages come out. So you may ask also, why are we focusing so much on thermal cycling as the primary tool in our durability life testing? Well, that's because thermal cycling has been found to be able to detect more defects and has been the root cause of more field failures than any of the other environmental stresses that electronics are exposed to, as is shown by these studies from the Institute on Environmental Stress Testing and at NASA working on aerospace and space products. So here I have the links to these two papers if anybody wants to look into this in more detail. So now in our simulation guided evaluation test process to correlate test duration to our desired or expected field durability life conditions, what we do in simulation guided testing analysis is based on the material science principles of stress-driven damage accumulation in materials, which can also be known as stress aging, stress-driven aging. So our physics of failure mechanism models are based on this principle to determine the rate of damage accumulation under stress cycles or stress durations, and when the failure point of an item is reached. We'll show this in the following slides. The procedure involves creating, like I said, a CAD model of the module circuit board assembly and all of its components in the Sherlock durability simulation program. And we first run the simulation using the model expected in-service field life operating conditions and stresses to determine the amount of accumulated damage life consumption the model will experience over its usage life. A second durability simulation is then run using the stress conditions the model will experience in the stress profile of your accelerated life test. So the results of the second durability simulation using the same device, product design model can then be evaluated to determine how long it takes for the test to accumulate an equivalent amount of stress aging, damage accumulation, to what is built up in the field lifetime usage scenario. And then we can use that to determine how long a higher stress level, faster accelerated life test needs to be run in order to correlate to the same amount of damage accumulation, damage degradation that would occur in the field life scenario. So to illustrate this here, the simulation guided testing process is for designing an accurate and optimized accelerated life test from knowledge of field conditions. So what we do here, as I just explained, is number one, we create the durability model of your electronic device in the Sherlock environment, and then we define what the field stress conditions and durations and exposure rates are. And this gives us this irregular curve of damage accumulation until we reach the point where the damage has built to where failures are being occurred. Now, of course, there will be a variation built around that from component to component. There's some folks who have tried to work with that, but mostly people are just looking at and using the mean component design and build metrics and using that to determine a mean time to field failure, damage accumulation. So then, that's when we then rerun the model now under the stress profile we want to see for our accelerated life test. And now in the accelerated life test, you see we can rapidly build up our rate of damage accumulation and see how long it takes us to get to the same damage metric. And then we look at how long it takes to get there, and that's where we can do our test to field correlation. The opposite approach to that is called simulation-aided testing, and this is where we've run the life test first in the accelerated environment, and we saw how long it took to get to the point of failure in the test. And then we use that point of failure in the test, and we rerun the model under the actual expected field conditions and see how long it gets to take to get to that point in order to correlate the life test to the field life. So a case study of this that we did here not too long ago, an OEM required a reliability of at least 97% or less than a 3% failure risk over a 10-year durability period for an electronic module. And they defined what they believe to be a thermal cycling reliability durability demonstration test that would reflect this 10-year life cycle. The supplier noted that this test was more severe than what they had seen for similar modules from the same OEM. But one of the things we're seeing is, with the desire to have more and better reliability, there's always the concept of, well, if we tested at this level before and got this reliability, if we increase the test level, maybe we'll get better reliability. And this isn't always true, and sometimes it leads us to that foolish failure situation, which is why we are here recommending that tests need to be properly calibrated and correlated to field conditions, which, as I said before, is a very expensive and long process that is not easy to do, so it doesn't happen very regularly. But now with the simulation-aided testing, we have the ability to do this more often and more easily. So the supplier did experience failures of their electronic module on the test, and this prevented them from getting approval to meeting the OEM's reliability requirements and get authorization to move forward into production. So the supplier contacted us at DFR and asked us to help determine what is the test to field correlation, what did this test actually demonstrate. And we used the Sherlock program and the simulation-aided testing process we just described. We created the 3D model of their electronic module in the Sherlock environment. And we set up an annual thermal cycling event based on the OEM's definition of the annual 10-year thermal cycling environment they were wanting to design. And when this was all done, we determined that the OEM's 10-year life test was actually correlated to 20.2 years of field life, and that the 10-year field life was actually achieved at 49% of the time into the test. And at this point, the demonstrated field risk was only 1.8%, which meant the reliability was 98.2%, which meant that it did meet their requirement of less than 3% failure risk. So what that looked like was the life plots that we came out of this under the test condition and the field condition. And we saw that under the test, we had a probability of failure of 13.8% at what was defined to be a 10-year life point. But when we ran that under the OEM's field definition, to get to 13.8% failure risk, took us to 20.2 years, not 10. And that's when we could then correlate that the 3% failure rate actually occurred at about 5.75, 5.8% of the time into the test, which correlated to just a little less than 12 years in the real world. And the point that did correlate to 10 years in the field environment was 1.8% failure risk that occurred at around 4.8 years, 4.8% of the 48% of the time into the test. 48. So from demonstrating this, the OEM did accept that the desired reliability demonstration had been achieved, and they allowed the product to go into production and decided to adjust their test requirements for future products. So what does it take to define the field environment? It's not just saying that, oh, this device has to operate from -40 to 180 degrees C or something like that. You need to know the time you spend in, each general temperature range. So this shows for an automotive device the time it spends at different temperatures over a 10-year life. And I'm sorry, but the time column is hidden here because this would be data that's we are not allowed to give out. And the same thing can be done in terms of thermal cycling in what we define as the peak and valley chart. So the valley temperatures are the temperature range that you experience at the cool part of the day, at night, or when a vehicle or the system is off and no longer generating power. And then the peak part is the hot temperature of the day you see from your climactic and seasonal and sun loading effects. So you can see here that there's a plot of peak here for temperatures that are in the 40 to 60 degree F range at night that heat up to 80 to 100 degrees F during the day. And if we move up that a little bit to this red tau peak here, we see that we got a number that represents how many times over 10 years the module would go from 40 to 60 degrees F to 160 to 180 degrees F. So this allows us to put these together into our model in order to apply the loads and environmental exposure stresses that we will use in the physics of failure durability simulation. So to show a few other aspects about accelerated testing, we can know from our research that acceleration rates can be correlated to the stress strain yield curve of a material. So as I mentioned earlier, if you got a material that's working in the elastic range that snaps back with every release of the stress strain, you're going to have this very long, near infinite life capability of that exposure or endurance. But eventually you crossed over into the elastic to plastic range, and that's where we get plastic deformation. And as we go higher up on the stress strain curve, we get more damage per cycle, which increases the acceleration rate of damage per cycle in our accelerated life test. So this is the useful range that we want to design an accelerated life test. Because if we take the test level up to stresses that get us into the yield point or fracture point of a material, that's when we get into this foolish failure region. And that means our stress levels are so high that we are no longer wearing out our products, we are breaking them. And breaking a product does not tell you anything about its true durability capabilities. And actually, we've seen this quite a bit on organizations that use the HALT, highly accelerated life test method, where you've got parts that are in a chamber with very powerful vibration and thermal cycling combined, and you keep incrementing the stress levels as you go through this test until failures occur. Well, when we do failure analysis of the failures on the whole test, the majority of them are breakage, overstress, fracture failures, not wear-out failures. So that can be considered that the name highly accelerated life test that Dr. Hobbs gave to this procedure isn't really the best name for it. I would prefer to call it a product ruggedization development process, because it tells you, what stress levels you will break the product on. And yes, a stronger product will also have a longer wear out or aging life, but you don't know how long until you correlate it and keep it within the wear out range and don't go into the yield fracture point. So some other physics of failure guidelines have been developed and published in documents such as IPC SM 785, Guidelines on Accelerated Reliability Testing, and in the book by John Law, Solder Joint Reliability Theory and Applications. So from this, we now know that in a thermal cycle, the primary aging factors are the high-end temperature, the high to low temperature difference, and the number of cycles. The second aging factors are the hot dwell time and the rate of change that you're experiencing as you go from hot to cold and cold to hot. Now, the limiting factors that you have to watch out for to avoid foolish failures are if your high-end temperature is too hot, if your rate of change is too rapid, and if you do not have a certain degree of hot dwell time. And these all have to be based not on the temperature profiles of the chamber, but on how the temperature changes and values are experienced inside your electronic product at the circuit board and its components. So additional information on this thermal cycle optimization is that you need to select a maximum temperature that does not exceed the glass transition temperature of the circuit board substrate material. The glass transition temperature is the point where the epoxy in a FR4 circuit board goes from being a solid to a putty-like material that no longer has a linear coefficient of thermal expansion, but now becomes an exponential thermal expansion factor as you get into hotter and hotter temperatures. You also want to make sure that the recrystallization temperature of any of the plastics used in the device is not exceeded. Now, temperature dwell time needs to be measured at the component. Hot dwell time is when damage actually occurs. It's more important than the cold dwell time. Because when you are cold, your material is virtually a true solid. It no longer is, solder melts at, say, 183 to 220 degrees C, whether you're using tin lead or lead-free solders. And as in the range that we use them, room temperature 20 to 80 to 120 C, they are actually getting very close to their melting point. And they become weaker and they fatigue and degrade faster when they're hot. But when they're cold, there's hardly any degradation at all. So when we develop a thermal cycle, it used to be, let's say you had a lightweight module, you could do a 15-minute heating ramp rate, and then a 15-minute hot dwell, and then 15 minutes to go down to cold dwell, and then 15 minutes of at cold dwell, and then you ramp up again. So that would give you one thermal cycle per hour. Now, suppose that you kept the 15-minute hot heating time, you kept the 15-minute hot dwell time, you kept the 15-minute cold dwell time, but suppose your cold dwell time was only 5 minutes, which would allow you just enough time to make sure that the circuit board and all of its components actually reach the desired temperature. So what that would do would allow you to do a thermal cycle in 50 minutes instead of 60. And when you look at the number of minutes you have in a day, there's, I do that right here, 24, enter 60 times. 1,140 minutes per day. 60-minute cycles, you can get 24 cycles per day. 50-minute cycles, you can get 29 cycles per day. So this lets you get more cycles in per day, which allows you to get your testing done faster. Because what's important is the number of thermal cycles you do, not how long you spend thermal cycles. And then here we show you how it's important to know the heating and cooling and temperatures of the board and its components instead of just the temperatures of the air in your thermal cycling chamber. If you don't reach these temperatures, you can't count on figuring out that degree of stress. You've got to figure out the actual hot to cold temperature difference the part actually experiences in the chamber, not what the chamber is set for. Another interesting fact in accelerated testing is we know now that thermal shock testing, where you have a part that is in a transitional two-chamber test equipment, where there's a hot compartment and a cold compartment, and a trolley or slide moves the samples back and forth rapidly from hot to cold testing. This produces very rapid ramp rates at the board. When they're at the range of 20 to 30 degrees C per minute, again, as measured at the circuit board, this is what's called a thermal shock condition. And when this happens, you are putting 1.5 to 1.8 times more damage per thermal cycle into your circuit board assembly and its solder joints than you would with a power temperature cycling chamber, where you have a single chamber that heats up and cools down the device much more slowly. And the problem is, though, in thermal shock, while we can get more cycles per day and more damage per cycle, we cannot have the unit hooked up and wired and monitored and operated to detect if it's performing properly throughout that thermal cycle when the first failures occur. And this is because the transition back and forth, you just can't handle the wiring moving that much. So what we developed was a process where you would want to design your test so that 1/2 to 2/3 of the life could be consumed under thermal cycling conditions. And then this would be treated, any failures that were, after you came out of that amount of thermal shock cycles, you would do a functional test. Any problems that were noted would be considered to be due to some kind of early life infant mortality quality defect that needed to be addressed differently than wear-out conditions. And then we would run the last half to 1/3 of the test under the power temperature cycling chambers, which would allow us to operate the unit, put in operational heat, as well as detect if any failures occur and when they occurred, so that we could use the time to failure in doing a Levell plot or other types of reliability calculations. Another issue to consider is how to deal with the effects of combined environment. In the real world, you don't just experience one kind of stress condition at a time. They're happening to you simultaneously. And this actually wound up being a project I had from GM Management, and we researched this, and the question was, if our parts are passing our life test, why are they failing in the field? And what I found out was that traditionally the life testing is set up to optimize the scheduling and efficiency of the test personnel and the test equipment. So I discovered there were separate mechanical labs, thermal labs, environmental labs, and a different set of components went into each of these labs. You got a certain degree of robustness that the components could endure each individual stress, but in actuality we found that different stresses could combine together to produce the same failure mechanism, and we were missing this critical interaction. So this led to new test formats where there were mixed environments based on physics of failure knowledge, where we saw that solder cracks or wire bond failures or lead fatigue was related to the range and number of thermal cycles the part was experiencing, combined with vibration and shock at temperature. And diffusion, which is the wear-out mechanism on a integrated circuit die, would be due to temperature and material interactions on the die. Organic growth issues would be time and temperature and humidity levels, and if there were organic contaminants present. Electromigration, dendritic growth failures, were determined to be a combined function of time and humidity, voltage and current, and ionic contaminants, and the geometry layout of the circuit board. Same thing with conductive filament formations. Short circuits like dendritic growths within the circuit board were traced to time and humidity penetration into a circuit board, the temperature, the voltage difference, the board material, the layout, and if the glass fibers left air gaps or had hollow fibers that allowed electromigration, electrochemical migration of copper to build up and form a short circuit trace. So all of this knowledge about the combined conditions that produce failures allowed us to move from single environment, environmental testing, to failure mechanism susceptibility detection testing based on combining the stresses that we determined were found to produce failure mechanisms. And an example of that is shown in this chart where we combine thermal strain in the solder joints and with vibrational strain. So here at the low thermal strain with low vibrational strain, you see a very long life that's in the elastic range, but eventually the vibrational strain comes up to a point where you start sliding down this curve. Here's your useful acceleration factor calibration information, but eventually you get to the point where it's so high that it's just shaking its apart. It's now at that yield point. If we double the thermal strain up from 1.5% to 3%, we now have a new curve much farther down because the 3% acceleration factor is now telling us something useful. And again, we can see the effects of adding vibration into that. If we come up to 6%, well, we're almost got zero life. This is kind of, the thermal cycle strain is too much, and we are yielding materials rather than fatiguing and wearing it out. So, as I said, in reality, environmental conditions occur simultaneously, and we would like to test simultaneously, but correlating a combined environment life test is very difficult. I tried because it's difficult to define the combination of two stress levels in the field of what's appropriate. And we got into a lot of cases where we had situations of foolish failure. So what we wound up doing was going to sequential testing, and this is also recommended in those environmental test specs I referenced at the beginning of this year, that you would like to run your most severe environments last in a test sequence. That usually means your vibration is shock. So I've had a lot of success where I use thermal cycling at the start of a test to condition the product and weaken the product, and then I apply vibration afterward to see if the product, after a lifetime of thermal cycling, still has enough strength to endure vibration conditions. I call this the shake after bake philosophy, and it has been very effective for us. So in conclusion, in this presentation, we've discussed how physics of failure knowledge and failure mechanism models and obtained durability simulation using the Sherlock ADAK lab can be used not only to produce a reliable design, but can also be used to produce an optimal application-specific accelerated life qualification test for your EE products to prove that the capable design is getting the expected part and assembly strength that was used in the design assumptions. So with that, I'd like to thank you all very much for your attention. And are there any questions, or if any of you would like more information or assistance in developing an optimized test plan, here's my email and phone number contact. So with that, Mark, do we have any questions popping up?
Yeah, and once again, thank you, Jim, for that great presentation. At this point, I see one question, but it is only the word question with a colon, so that's not going to, that's not an actual question. Looks like we have another question here. How can we have the slides? So I'm going to go over that at the end. of this presentation. And another question just popped up here as well. In Sherlock, is there a standard usage profile?
Well, we have developed and built in libraries of some of the tests from automotive and military, but usually those conditions define the test chamber settings. And so I have actually found it better to actually characterize the way a specific product responds to temperature and vibration and then use that in there. And we have the ability in the Sherlock profile that once you develop a profile of test field conditions, you can save it and reuse it yourself based on what you're designing and what products for what type of application.
All right, thank you, Jim. Another question about Sherlock here, and it is, can Sherlock be used for mechanical assemblies?
No, Sherlock is specifically set up to look at and have libraries of electrical materials and models of electrical components. And one of the reasons we can do this is, I like to say that electronics is like your kids' Lego toy sets. You know, you got these different components, blocks, in different form factors, sizes, and colors, and you put them together in different ways to get different features. But it's the fact that there are these very standardized families of integrated circuit packages and chip resistors and chip capacitors and lead capacitors and middle film. The organization known as JEDEC, the Joint Engineering Design Electronic Council, Joint Electrical Design and Engineering Council, JEDEC. They're the folks who qualify and prove a family of electrical components to be in certain form factors and sizes. And this is important because our circuit board assemblies are no longer assembled by people with very small fingers plugging components into holes. They are now assembled by virtually robots, your chip shooters, your pick-and-place equipment, your automatic reflow soldering irons. You put a circuit board on at the start of an electronic circuit board assembly line, and it's never touched by human hands until it comes off at the other end. And so this requires very precise consistency of the component packages, their size and their tolerances, which need to also go and correlate to a set of IPC standards that define the recommended land patterns for various types of components. So this is what enables today's electronic assembly technology. Now, with mechanical components, a spring or a shock or what, you can design that to be any size you want for your specific application. It's not like these parts are highly standardized. So that's why we have been able to build a CADE app that automates design creation. It's because of the fundamental standardization of all the various types of electrical components. Hope that answers your question.
All right, Jim. Thank you very much. And it looks like that is all of the questions that we have. So to go back to that other question about the slides being made available, just to go over that one more time, if you would like the slides immediately, go ahead and email Jim at his email, which is on screen. He will forward that to me, and I will get you the recording of the presentation immediately.
Well, you'll get them the slide set. The recording is going to take a day or two to process.
Well, that's true. Yes, you're right about that. And then from DFR, so what we'll also do is we're going to put it on the DFR website as well within a few days. That'll be the full recording, and you can download it there if you'd like to in a couple of days. So that's dfrsolutions.com. And seeing as we don't have any other questions, I'm going to go ahead and wrap up the webinar. So thank you, everyone, for joining us today, and have a great day.
Thank you very much, and you all have great holiday season coming up here. Good day.